Okay, hello everybody. I'm Alex Heaton from Max Planck and TU Berlin, and my task is to moderate with questions for the speaker today. And so if you have any questions, type them in the chat and I will interrupt. But without further waiting, Laura Colmenarejo from UMass Amherst will talk to us about signatures of paths, the shuffle algebra, and de Bruijn's formula.
Thank you, Alex. Thank you all for being here. I assume most of you will be probably in Germany or Europe. So just give me a little bit of mercy. It's 8:30 here. My brain may take a little bit while if you ask me a question and I need to think about it. So I want to present this work. I worked on this problem when I was at the MPI with Joshua. So I'm very happy to talk about it in this seminar. And I wasn't sure if most of the people knew about signatures and paths, so the introduction is mostly on that. Okay, so the way that we think about a path is going to be very simple. Probably many of you will think that I'm simplifying things way more than I should, but for me it's just going to be like a smooth path, a continuous map from the 0-1 interval to the R to the D. And it's a very simple mathematical object if I just try to talk about to someone about it. And it has like, it's a very good tool if you try to modelize things with it. What is the problem? That is a continuous object. So when you try to do explicit computations, that is going to be very complicated to handle. So one of the ways we do in math to solve this kind of problems is to find invariants. And what Chen did in the 50s was to introduce an iterated integral signature for a path that is for me, at least as far as I know, is mostly a stochastic analysis area. I don't know why. Yeah. No. So when I talk about a path, I'm going to call it a good path, so I don't have to worry about integrals or if it's or any other problem that I may have with my computations. I want everything to go smooth. So the notation I'm going to use is upper indices for the coordinates, and I'm going to define. But I'm going to assume also that they pass through the origin. So what I'm going to do is I'm going to take a sequence of numbers between 1 and D and length k, and I'm going to define this iterated integral over here. This one. It's a little bit weird, the highlighting, but I hope you can follow. Is everyone familiar with the iterated integral, or should I go through it? There's one yes, and I will go through it. If not, I assume like you will know what I'm doing. So this iterated integral is taking the derivatives and it's computing. At the end of the day, it's just a number. So what we want to do is we want to keep all the information for all the possible k's and all the possible sequences. And I'm going to keep this information in 2 different levels. If I'm fixing the length of the sequence, then I'm going to talk about the kth signature of x. And initially, I'm just going to write it as a sequence with some order on my sequences. And if I'm keeping all the information for all the k's, then I'm going to have the signature of the path. And I'm just taking the 0 signature as 1.
Actually, can I interrupt with a question?
Yeah.
The t's, so you're not integrating to 1 everywhere. You're also choosing the t's and the i's.
So I'm only choosing the i's because this integral is independent of the t's. I'm going to get at the end of the day a number. So when you do the integral between 0 and t2 of the first derivative with respect to dt1, you're going to get something depending on t2. And then you integrate with respect to t2 and you get t3 and so on. So at the end of the day, it doesn't depend on the t's. So those are, okay. I just take them as variables.
And then if you chose the sequence 1, 2, that will give you a different number than the sequence 2, 1?
Yes, and let me give you an example for that. Let's actually compute some integral. So I'm taking a path, a 2-dimensional path, and I'm taking as the first coordinate t and the second coordinate t squared. So if I just have sigma of 2, I'm just taking the second signature. This is basically the fundamental theorem of calculus. I'm having the integral between 0 and 1 of the derivative of the second coordinate. So the 2 here of the signature corresponds to the 2, to taking the second coordinate in my integral. So if I compute the derivative of the second coordinate, I have 2t. I have to evaluate it in t1. So I'm gonna have 2t1 between 0, integrated between 0 and 1, and that gives me 1. Now, if I have 1, 2, what I'm doing is I'm taking 2 iterated integrals. One goes from 0 to 1, and the other one from 0 to t2. And I'm taking the first coordinate and the second coordinate derivatives. But like here, the order will matter because the first one is evaluated in t1. So this part over here does not affect the first integral. So I'm just taking, let me do it this way. I'm taking this part over here and I'm integrating. Since I have 1, this integral is just t2. So that's why I have a t2 here. And I now have to consider the second coordinate, the derivative here. And I'm gonna put all together and I get a number. So that's why it doesn't matter the t's. I can treat them as variables, and at the end, since the last integral is between 0 and 1, it will give me always a number. One way to think about this, I think it's like, it doesn't matter how fast you go through the path when you integrate. So that's why it's not relevant at that point. And if you're doing with 3, then you just have to like continue doing these integrals. And eventually you get the numbers. So if I want to keep this information in this example, I will have that sigma 2 is 1, sigma 1, 2 is 2/3, and sigma 2, 2, 2 is 1/6. So I can actually give you the signature of x. So I'm going to encode that information in another way. So sigma of x, I have the 1 for sigma 0, and then I have 1 times 2 plus 1/2, 1, 1 plus 2, 2, etc. So I was preparing an online talk, so that is always a good joke. I can say like, okay, I told you at the beginning that I'm going to store the information with the signature with a sequence. I'm not writing a sequence. So let me explain you how I'm going to encode the information for the signature, and I'm going to use words. So I can associate these coefficients to each of the sequences. And for me, the sequences are words. So this is a more combinatorial perspective. So let me show you the framework. So I have my sequences and I have my integrals. So what I'm gonna do is I'm gonna consider the set of words of length k. So these are my sequences in the alphabet D. So I'm just taking the sequences and consider them as words. And what I'm gonna do is for each of the words here, I'm gonna compute the signature and I'm gonna put it as a coefficient. And for the 0 signature, I just have the identity, the empty word. So for the example that we were doing before, I have the 1 times 2. This, I'm treating this as a word, while this other one is a coefficient. So it's clear how I'm encoding the information of the signature. Yes, no, I don't see faces, so. Okay, so good. Okay, so this is so we. Oh, I changed the not the notation, but how I'm highlighting things. So now every time you see something in blue and bold, those are gonna be words. So these are the ones. Wait, this is no, it's not giving me. This is my coefficient now, and these are my words. Okay, so I need to explain you what is the setting for words. So we're going to consider two settings, two spaces. The first one is going to be the space of formal power series in words in the alphabet 1 up to D. And I'm going to consider as the operation the concatenation product. So I'm taking two words and I'm just putting them together, one after the other, in the order that they appear. So W dot V is just going to be putting the word W and V together. The other algebra that I'm going to consider is, instead of formal power series, I'm going to consider a set of polynomials. Again, in words in the same alphabet. But now the operation that I'm going to consider is called the shuffle product. So what I'm going to do is I'm going to shuffle all the entries of W and V, keeping the order in which they appear. So let me give you an example. If I have the word 1 and 2 and 3, 4, 5, so this one here is my V. When I concatenate them, I just get 1, 2, 3, 4, 5. But when I shuffle them, what I have to do is I have to shuffle the entries 1 and 2 and 3, 4, 5, preserving the order. So I will have, of course, like I can just put them together, or I can mix the 3 between the 1 and 2, and I will get this other one. And I can continue. I can continue doing this for all the entries that I have. So the ones that appear here are the ones that have 5 at the end. But then eventually I can be moving the 5 also in between. So some comments about these algebras is that, well, the first of all, the one in which I'm considering formal power series is a non-commutative algebra, because the word WV is not the same that if I multiply them in the other order. While if you think about the shuffle, since I'm shuffling in all the possible ways, preserving the order, that is going to be commutative. And is in most of the cases is called the tensor of the shuffle algebra, that it was in the title. I can grade both of the algebras by the length. And then I also have a dual pairing, because these two algebras turn out to be dual. And what I can do is, if I have a formal power series on the left, and then a word on the right, this will just give me the coefficient of the word V in the formal power series. And I can just extend this by linearity to any other polynomial that I can have on the right.
Laura, can I ask another question?
Yeah.
This is Alex. On the previous slide, you had grouped some terms together, like 1, 1 and 2, 2. Both have a coefficient 1/2.
Yes.
Is there like going to be a lot of situations where we already know the coefficient's going to be the same for different words?
I think this is just a coincidence. For instance, if you look at 1, 2, and 2, 1, one has a 1/3 and the other one has 2/3. So I think this is just a coincidence.
Okay, so there's no meaning to infer from there. Okay, thank you.
No, there is no meaning so far.
Okay.
Okay, so if you wonder why these algebras, from the signatures point of view, it's very kind of like obvious, and it's because the signatures behave well with these two operations in the following way. For the shuffle, we have the shuffle identity, which means that if I'm shuffling two words and taking the coefficient of the shuffle in the signature, is the same that multiplying the coefficient of each of the words in the signature. So this multiplication over here is multiplication of real numbers. So in this sense, the shuffle behaves very well with respect to the signature. For the concatenation, what we have is the concatenation of paths. So if I have two paths, then I can just concatenate them, put one after the other, and just make sure that I'm still having, like if I want to be consistent with the interval at 0, 1, that is not very relevant. But what happened with the signature of this concatenated path, the concatenation path, is that it's actually the concatenation of the two signatures. And this operation over here is the concatenation of the words. So you will just concatenate the two signatures. If you
can I ask another question? Yeah. Concatenating the two signatures, does that mean concatenating each of the coordinates?
Yes, you will go term by term. It will be like multiplying to formal power series. Remember that you can keep the signature as an infinite sum. You will just be multiplying term by term.
I see. Thank you.
And if you ask me, because I consider myself a combinatorialist, why these three structures are good is because if I just restrict to one of the algebras, I will have a half algebra structure, and that's really good. If you get to a point where you get a half algebra, which basically means that you can have like a product and co-product that behaves kind of like the concatenation and the shuffle product, then you will have some extra properties that can kind of like for free. And this structure is very good and very compatible with many other operations that you may have. So why I'm interested in signatures, this is probably one of the slides that you are more aware of. Is an old topic in stochastic analysis. And by all, I mean there are already a couple of textbooks. And I think that is a good way of measure when something starts to become old. But when I arrived to the Max Planck Institute in 2018, Bernard Sturmfels with Max Pfeffer and Anna Siegel, they were already looking at signatures as tensors, more in a data science setup. And they were trying to they published a paper in which they were answering the question in which you're given information of a signature and you want to recover the path. So if you think about the signature as an infinite sequence or a formal power series, you are eventually you cannot store all that information. It's going to be very complicated. So maybe you can only access part of that information. Can you recover the path? Jorsa and Jeremy, on the other hand, they gave a more combinatorial approach to understanding variants of multidimensional time series. And they based, the result was mostly simplifying to signatures of paths and then find the connection with the representation theory. And that was something that for me was very interesting. And then the other paper that when I arrived to the MPI was bring to my attention was how Bernd Sturmfels with Carlos Amendola and Peter Fritz, how they were able to define a variety structure on signatures for some particular paths. The point was you were having something that initially is very analytical with integrals and everything, and they were able to define a variety. So that was very interesting. And what I did was 3 projects that are kind of related somehow. With Rosa Priest, who is a graduate student in TU Berlin, we look at what happened with the signature of a path when you transform it by a polynomial map. So you have a path, you apply a polynomial map, and you obtain another path, and you want to relate both of the signatures. And we did it using half shuffles and symbol algebras. And these other 2 papers are the ones that I'm going to talk a little bit about today. So the first one was with Francesco Galuppi and Mateusz Michalek, and it was continuing this work of Carlos Amendola, Bernd Sturmfels, and Peter on the varieties, and we look at some toric geometry of paths of the varieties. So we look at the signatures varieties for path, and then also for axis parallel paths. And what happened is that we have a determinant result. That is the one that I want to present to you today. And as a continuation of that, at the time I was also talking with Josa, and we realized that we could somehow generalize this determinant result to other settings. In this case, it's going to be the setting of shuffle algebras. And together with Stefana, we were able to give a proof and then give an alternative proof of the Bruijn's formulas. And that's what I want to introduce to you today. This paper, I think, I don't know if when you update it, but we updated today to a better version of the paper, in case you're interested to look at it. Okay. So the first thing that I want to do is I want to give you an idea of how to compute the signature for an axis path in a very combinatorial way. So if I have an axis, what I consider an axis path is I'm gonna take steps, and each of the steps is gonna be parallel of one of the axes. So I can basically concatenate m paths in which each of them is just a multiple of the vector in the standard basis. So this E is the standard basis of the dimensional space, and this A's are just like the length of the step. So when you concatenate all of them, you are gonna get an axis path, an axis parallel path. And the way that I want to think about this is, well, I don't need to keep the path, like all the information as a concatenation of other paths. I can just tell you what are the length, the A's, and I can just tell you what are the directions. So I just need the VI's over here and the A's. So that's how I'm gonna characterize my path. I have the sequence of length that is telling me how long is each step, and then the shape of the path that is gonna keep the track of the directions, the V's over here, the news. So actually, I want to keep the shape to storage the information of the shape in a slight different way. So instead of just keeping like the first, so for instance, this one over here, this is telling me that the first step is in the direction 1, the second step is in the direction 2, the third step is again in direction 1, and so on. So instead of keeping like in order, what I'm gonna do is I'm gonna define a set partition, which is basically telling me what things, like which steps are in the first direction. So in the first direction, I have the first step, the third, and the sixth. So that's why I have a 1, 3, 6 here. Now in the second direction, I only have the second step. So I have a 2 over here. And in the third direction, I have the fourth and the fifth. So I have 4 and 5 here. If by some reason I don't have, imagine that these two were 4s, I will have just an empty here and then 4, 5. So the same way I can do this one, if I'm, for instance, like adding this 4 over here is in the 8th step. So that's why there is an 8 over here. So if you know the length and you know the shape, it doesn't matter if it is just as a sequence like this one or is a set partition like this other one. You're gonna have all the information of your axis path. And that's all you need to compute the signature. So our result says that if I give you an axis path, for nu I'm gonna denote the direction, and for pi the set partition, in case you don't understand the notation at this point. So what I'm saying is, if I fix a sequence of i's and I look at the signature, this is gonna be this formula over here. I'm gonna sum over all non-decreasing sequences, says that the j's are in the corresponding direction, and then the s's are just counting how many repetitions do I have. So let me show you with an example, because it's easier to describe the formula. So from my perspective, because the idea of finding this formula was more into going for varieties, I'm not gonna fix some lengths, so I'm just gonna let them as variables. So I have A1 to A8. This is gonna be the sequences of length, and then I'm fixing the direction. So I have this example over here, which is I can have the new or the set partition. So what I'm doing is I'm gonna sum over all the possible ways of finding something in the first place, like in this example over here. The sequence is gonna tell me in which sets in the set partition should I be. So if I have 1, 2, 3, 4, I need something from the first set, the second set, the third set, and the fourth set, such that the labels are increasing or non-decreasing. So I can have, for instance, 1, 2, 4, and 8, and that will give me this term over here. Or I can have 1, 2, 6, and 8, and I have this other one. For instance, if I want to start with 3, then I could take 3, 5, 6, and 8, and that will give me the last one. But if I want to start with 7, then I do not have increasing labels in the next 2 sets. I only have 8, so I cannot have such a monomial in my signature. if, for instance, another example, when I get 0 is if I have 4, 1, 2, 3. So that means that I need to take something for the last one, and then 1, 2, and 3. So if I take something from the last one, I'm taking an 8, and there is no larger labels in the other 3 sets, so I cannot get any monomial here, so I get a 0. Let me delete all of this. And now let me show you where the coefficients are coming from. So in my sequences in the signature, I can actually repeat entries. So I can have 1, 1, 2, 4. This means that I need to take 2 entries from the first set, something from the second, and something from the fourth one, in such a way that they are increasing. So in my formula, there is no restriction for me to take the same entry twice. So I can take 1, 1, and then 2 and 8. And that will give me this term over here. But since I'm repeating the 1 twice, I'm going to have 1 over 2. It's actually 2 factorial. But imagine that if I have 3 1s and I'm putting a 1 to the third, then I will have 1 over 3 factorial. So this coefficient over here is kind of like keeping track of things that I'm repeating. So it's more or less clear how are we computing this signature. It's a little bit tricky at the beginning, but I don't know. For me, it was like the way I understood the formula at the beginning, and then I realized that it was like actually like a nicer description than just computing all the integrals. Okay, I don't see questions, so I'm gonna continue.
To me, it was really clear when you explained it. But also, we're about halfway through, and
okay.
I was told maybe we can maybe this is a good spot to pause and just let people think. Do they have a question?
No. Okay. So coming back to the question about what we were doing, we were thinking about varieties. So but what we wanted to know is, like, if you think about a variety, we wanted to define them using polynomials. So we want to find relations between the entries. So the relations that we were looking for are relations on the signatures. So we were like thinking about that. And then at some point I realized that the second signature can be actually be written as a matrix. So you can storage like your sigmas, since you have your words 1, 1, 1, 2, etc. You can just put it as a D by D matrix. So an obvious question is like, okay, will the determinant give us extra useful information? And it was like, well, maybe let's do some experiments. Since we have this nice formula for the axis path, it's very easy to compute it with a computer. You just have to, like, you will just give these 2 things and it will just give you the polynomials, and then it was easy for us to do computations. So what happens is that when you compute the determinant, it's actually a square of a polynomial in the A's up to some scalar factor. So let me put you the result, because that will be more clear. So if you have an axis path in the d-dimensional space, this is the factor. Up to this factor, the determinant of the matrix that I just showed you is actually this P of A, this polynomial square, where this polynomial over here is basically like a product of the A's with some subsequences. So we were actually able to describe the polynomial. We were able to find which polynomials were giving us this nice description. And I'm not gonna spend a lot of time talking about the polynomial itself. I can just tell you that the proof was very technical. It was very like related to the description of the axis path and the signature, and it took us a while to be able to understand why this was true and why we were getting this description. So the proof of this theorem is super technical, but there is a way to understand this in the shuffle, in terms of shuffles and the shuffle identity. So let me give you an example of how to compute this these polynomials, this P of A. So you have, this is an example in which I chose a sorted example for in this case. Instead of having 7 or 8 entries, I only have 6 because that would be nicer for that's the only way that the matrix is gonna fix in the slide. So I have this path that I can write with the sequence of directions of the set partition. And I want to compute this determinant. So what I'm gonna do is I'm gonna be looking to subsequences I have here, I1, I2, I3, and those are gonna be subsequences of each of the sets in my set partition over here. So I need to pick something, yeah, I need to pick something from, I'm messing with this one now. We're gonna choose monomials, and for each of the, okay, yeah, I'm gonna be taking like subsequences of the 1, 3, 2, 5, and 4, 6 in increasing order. So I can have 1, 2, and 4. I can have 1, 4, and 5. I'm just like in the first entry, I will have something in 1, 3, something in 2, 5, and something in 4, 6. And then what I'm keeping track is the permutation over here is telling me where was this element from. So if I have 1, 2, and 4, this is something from the first set, something from the second set, something from the third set. So that's why I have 1, 2, 3. If you look at 2, 3, 4, the 2 was in the second set. So I have a 2 here. The 3 is in the first one, and the 4th is in the third one. So I have a 2 and 3. And this is a permutation, and then I can compute the sign. So I'm gonna do this for all the possible subsequences, like increasing sequences. And then I will have the factor, and then I will just multiply the a's corresponding to each of these set with the sign. And that will give me the monomial. And I'm missing a square here again. So the determinant of my matrix is gonna be up to this factor, these monomials, the sum of these monomials squared. Okay. But then we were thinking, okay, this can actually be seen in a different way. If you put your signature, you had your second signature, you compute it as a determinant, you span it. We start realizing that this was actually, this term over here is taking the coefficient of 1, 1 in the signature of x. This is the coefficient of 2, 2 in the signature of x, etc. Now we can apply the Shuffle identity, and then these two terms will become 1, 1 Shuffle 2, 2, and this other one will be 1, 2 Shuffle 2, 1. But again, this formula can be seen as taking 1, 2, and 2, 1, and then shuffle it with itself twice. So we were like, okay, this is actually coming from somewhere else. And then we realized that, okay, if you look at this term over here, this is actually related to some invariant theory. So this is like, if I define the D invariant as the sum of all the permutations of D with the sign of the permutation and then the permutation itself. So here I will have 1, 2, and 2, 1, which are two permutations of S2, the symmetric group with only 2 elements. And then the positive and the negative are coming from the sign of the permutation. This is actually, like the result that we had before is actually saying, okay, so what you are doing is actually taking the square of each of the coefficients of this invariant, this D invariant, on the signature of the path. And then you square it, and then you get the determinant up to some factor. And that was just like at the point from the previous result, this was just like a consequence. Once we define everything and we do this argument in general, that was just like a consequence. But then Josa came and say, wait, this may be general in the Shuffle algebra. So this is a more general version in the sense that we are now gonna forget about the path, and we're just gonna have an identity in the Shuffle algebra. And the identity is the following. If you think about the matrix that I was having before, I was having signatures here. For each of the term, this 1, 1 was actually the signature element associated to the word 1, 1. So now we're gonna forget about signatures. There are no paths, there is nothing. So we just have this matrix in which it's a matrix with words. And I can compute the determinant of this matrix using the shuffle product. So every time like you think about the computing the determinant, but instead of multiplying numbers, you're gonna shuffle words. So then this result will make sense. But then we ask, like the question is like, can we prove this without having to go to signatures of paths? So in order to be able to prove this result, we needed to understand better what is the D invariant. And we're gonna do it from another perspective. The perspective we are gonna look at the invariant is through the representation theory. So this is very handled, like one-to-one with the results of Josh and Jeremy when they were looking at the SL invariant. So what happened is that well already studied this invariant, and the basis is indexed by standard jam tableaus. If you're not familiar with them, I'm just gonna say like, you have some shapes. In this case, we are gonna have only rectangular shapes, which is in this case, for instance, is 2, 2. But you can actually have like any sequence of decreasing or non-increasing entries, and you will just put as many boxes as you have in your sequence numbers, and then you are going to fill them with the numbers 1 up to D or 1 up to N, as many numbers as you need, and your conditions are going to be that you have to be strictly increasing in the rows and columns. So that is more or less like the idea behind standard jam tableaus. A standard one means that you do not repeat numbers on your fillings, and jam tableaus will mean that you have that your entries are increasing in rows and columns. So there is a way of reading a word out of a tableau, and the way that you do it is you look at the things that are like these numbers. The numbers in the fillings are going to tell you the positions of the things in the first row, the second row, etc. So I'm going to associate to the first row the letter 1, the second row the letter 2. So I have a 1 in position 1 and 2, so I have 1, 1. And I have a 2 in positions 3 and 4, so I have 2, 2. So the basis is indexed by standard jam tableaus, and then the basis itself is the invariance of these tableaus, which is basically saying, okay, you take the sum over all the possible permutations, you have the sign, and then you apply the permutation to the word associated to the tableau, but you only do it for those permutations such that the values in each columns are unchanged. So let's do the example that we had before. We realized, like we already saw that for T, for this one, the word is 1, 1, 2, 2. So that's what I have over here. And now I have to see for which permutations I'm considering here. So I need all the permutations that do not change the entries in the columns. So I can have the identity always, and then I can have only the permutation that change 1 and 3, and only the permutation that change 2 and 4, and then the permutation that change both of them. So that will give me this term over here. So our main result in this sense is that if you compute the determinant of the matrix that we had in the beginning, this is actually computing the invariant for the tableau with 2 columns and D rows, or 1 over 2 to the D, the invariant of the shuffling of just a column, the invariant associated to just a column of the entries. So let's see this with an example. So if I compute this determinant, this is exactly the formula that we have over here. And we saw before, we saw this equality before. It's just the way I was defining the invariant. And if you think about this other one, this is just when you have, you're gonna have 1, 2, and 2, 1, and you're gonna shuffle with itself twice. And that's how you get this result over here. Now proving this result was a little bit more interesting than I thought at the beginning, I have to confess. And the way we did it was in 2 steps. The first step is proving the first inequality, going from the determinant of the matrix to the invariant of the two columns, standard Young tableaus. So the way we realize about these formulas over here is basically that we did the case for d equals 3. There are a lot of cancellations. There are a lot of ways to try to explain it. But we found a really good one when it comes to talking about Haushoffel and concatenation products. And one of the keys was to keep the letters instead of 2, of length 2. So we were putting, if you notice this description over here and this one over here, I'm always having words of length 2. So keeping those words of length 2 was a key step for us in order to understand how the proof was going. And then what we did was just generalize the argument for any d. The other case, when we go from the invariant of the 2 columns to the invariant of only 1 column and shuffling it, was way more interesting. And that is because it's we had to involve some representation theory. So here we are talking about invariants. So what we proved was that these 2 terms, these 2 invariants, lie in the same one-dimensional isotopic component of a representation for some subgroup. So the subgroup that we were considering was this one over here. And what we did was to prove that these 2 terms lie inside this this component. And another detail is that the sign that we have in the invariant is also related to the sign of the representation here. And then we just needed to, once we know that both of them are in the same isotopic component, and that this one is one-dimensional, we just needed to figure out the prefactor here. And to do so, we just look at a particular word and figure out which one was it. And then when we were looking around the literature, we realized that this was related to the Pfaffian. So if I have a skew symmetric function matrix, over a commutative algebra, the Pfaffian is going to be defined with this polynomial, which is if you think about it, it's very similar to the polynomial that we were having for the axis path. I have exactly the a's here and everything. So it's not that surprising that this appears. And it has the property that if you compute a determinant of the matrix, is actually the square of the Pfaffian. And here there is just a recall, because we're gonna talk about our results. So if you have a matrix, you can always write it as the symmetric part and the antisymmetric part, this way over here. So our result was basically saying that if you compute the invariant of just the column, you're gonna have up to a factor the Pfaffian with respect to the shuffle product of the antisymmetric part of our matrices. So what this is, I put an example here, but this is actually one of the steps in the proof that we needed to solve, and is that if you have this determinant, this is actually the same that computing the determinant of this other matrix. So if you see here, this is the antisymmetric part of this matrix. So these 2 determinants are actually the same, and this is one of the steps in the proof. It's not an example, but it's almost like the interesting part of the proof. And this was in the even case, because the Bruijn's formula has 2 cases: one description for the even case, and then for the odd case is even more interesting, because you have that the invariant of 1 column is the Pfaffian of this matrix set, and this matrix is defined you put 2 times the anti-symmetric part of our original matrix, and then you just put a column with 1 up to d and a row with -1 up to -d and a 0 over here, and you still get the same result. So in this case, the middle step in our proof was to prove that the determinant of this matrix over here is actually the determinant of this other matrix. When here I have like 2 times the antisymmetric part, and then I have the -1, -2, -3, 0, and 1, 2, 3. So this is this matrix for d equals 3. And we had to show that actually these two matrices were, they had the same determinant. And that was all I had.
Okay, thank you very much. That was really interesting.